How's it going, everyone? So back in 2013, I was working as a junior project coordinator on a large nuclear power project in Ontario, Canada. And I was invited to watch a documentary about Admiral Hyman Rickover. This man led the development of the first nuclear powered submarine back in the 50s. Just imagine this. In 1945, we had Trinity, the first detonation of a nuclear weapon. In 1951, we had the first nuclear power plant. And then in 1954, just 9 years after Trinity, USS Nautilus, the first ever nuclear powered submarine, the one you see in this image here, enters service. In just 9 years, we invent nuclear engineering, create the nuclear supply chain, design and built the first nuclear power plant, designed the submarine, constructed the submarine, and put it into service. I mean, it's just crazy. It's made all the more incomprehensible by the fact that the nuclear Navy has like an impeccable safety record. I think they've gone like 250 million kilometers without a single radiological incident. Hyman Rickover, the guy that spearheaded all of this development, was intensely anti-automation. He hated automation. He fought to keep it off of his submarines. He fought like crazy to keep it out of the power plants. He said that if a crew member wants to start a pump, they should go to where the pump is to turn it on and to do it manually, so that if it's smoking, vibrating, grinding its bearings, the person would be able to see that and do something about it. He said that automation makes people dumb and lazy. Like, look at how upset he looks here. I'm a machine learning scientist, and I use artificial intelligence to automate things. So when I hear about the success of Hyman Rickover and his hatred of automation, it makes me wonder, like, is automation really a good thing? Or is it actually a bad thing? On one hand, nobody can dispute that people with adequate time, resources, skills, incentives, doing things manually will do things right and get things done. But I believe that automation is not only good, but it's urgently needed, and I'll tell you why. A lot's changed since the 50s. Builders now, more than ever, are contending with mountains of considerations beyond just the technical. In my city, Toronto, Canada, we have a major traffic problem. And we've been trying to expand our public transportation system like forever. In 1986, a subway running across Eglinton Avenue was first proposed in a transit network plan. The subway is only just about to be put into service. It's taken 40 years for the city to wade through all of the public consultations, regulations, litigations, interest groups, political and bureaucratic fragmentation, and funding issues. And it's hard not to hear stories like this and ask, have we become paralyzed by red tape? Because of all of this red tape, we're drowning in information. The Ontario Line Subway project in Toronto has collected over 15 terabytes of reality capture data. It's all being collected in an effort to complete the assessments, surveys, studies, plans, consultations. 15 terabytes of data. And this is just the beginning. Like, the amount of sensors is going to increase, connectivity is going to increase, data storage is going to increase. And if history is any guide, the red tape is also only going to increase. And all of these new information technologies are going to continue to drown us in data in an effort to meet the demands of the red tape. With all the world's problems, I don't think we can afford to be slow. We have to be faster. We need to be more agile. Information technologies like automation change the built environment in very tangible ways. I'll just mention this one thing because I think it's super interesting. What do you think makes tall buildings possible? I mean, of course, it's things like steel. And of course, there is the elevator. But let's consider whether tall buildings would be possible without the telephone. Would buildings have grown to hold so many people, so many businesses without it? Just like try to imagine the chaos of hundreds of human messengers cramming into elevators, navigating lobbies and offices. The telephone isn't just a communication device. It's fundamentally changed the way businesses operate and how buildings are used, making tall buildings viable. My contention is this: in the same way that telephones made buildings taller, automated processing of reality capture data will make buildings and the built environment much more agile. The floor area of a building is an important quantity. The company I work for, Integrated Projects, uses floor areas to price our Scan-to-BIM services. For every project we receive, the first thing we do is verify the square footage of the building represented in the point cloud. We're processing on the order of 6 projects per day and have ambitions of doing much more. So this verification process is something we were very interested in automating. Instead of opening up a point cloud and manually tracing out all of the floor areas, could we do this somehow without any manual human intervention every time a new order is received? Over the next 20 minutes, let's speed run through the development of a machine learning system that performs floor area estimation. And I'll explain a lot of what we learned along the way. The first step in getting a machine learning initiative off the ground is understanding what the technology can and cannot do. Now, I'll be honest, there's a tendency to overhype the tech. In reality, it's just a tool. Some tasks, especially in reality capture, still need human expertise or traditional software solutions. ML can't and shouldn't replace everything. So what should be automated with ML? There are a few criteria that should guide your investigation here. Look for tasks that are repetitive, where the cost of wrong predictions is cheap. They should be tasks you want to perform at a large scale, and the cost of maybe labor is prohibitive to that scaling, and where the patterns in the data being interpreted in performing the task are complex. Our floor area estimation task matches all of these criteria. We do it for every project. A couple hundred square feet of error in either direction won't make or break us. We want to be able to process dozens of large point clouds a day, and the patterns that distinguish building floor areas from not floor areas, such as exterior site space, can be very nuanced and complex. So how do we apply machine learning to automate the task? You should always start your ML journey by using existing neural network architectures. Don't develop something from scratch. In order to adopt an existing architecture, you'll need to frame your task as a task performed by one of these existing architectures. Existing architectures can do all kinds of things. This is semantic segmentation, where neural networks identify individual objects and their class, think like chair, table, window, wall. And this segmentation task can be applied to a number of things: modeling, defect detection, progress modeling, change detection. There are also more like specialized architectures for doing things like point cloud noise reduction, registration, and alignment, even in environments where things are changing. And one of my favorites that I don't really see talked about very often is something called point cloud completion, where you take a point cloud that maybe has very severe occlusions, feed it through a neural network, and it will fill in all of this missing data. At a high level, machine learning is an approach to learn complex patterns from existing data and use these patterns to make predictions on new data. The great breakthrough of machine learning is that we don't have to explain to the computer what patterns it should rely on when performing these tasks. Instead, it learns these patterns directly from examples provided in a data set. There are many approaches to data. Fundamentally, training data is just a bunch of input and output pairs. What are you going to give the neural network, and what do you expect in return? During my PhD, I hand labeled thousands of these kinds of input-output pairs, some that you see on the screen here. Hand labeled data is created specifically to train artificial neural networks. I labeled this data specifically to train neural networks. There are a bunch of platforms to do it. A lot of companies are willing to do it for you, but it's expensive and it is slow. I will strongly advise against this kind of data early on for many reasons, but mainly because if you have to hand label the data, the task you're trying to automate is likely not part of your business's core competency. And there's a high chance that things are just going off the rails for you strategically. I would strongly encourage you to instead find those tasks within your business that have natural or inherent labels. This is data that has labels being created as a byproduct of your standard business process. If you can find such data, it's a strong indication that this task is related to your business's core competency. In the case of floor area estimation, integrated projects has plenty of inherent labels. The building information models we deliver to customers as standard business process have floor slabs modeled and embedded floor areas we can pull from. There's no hand labeling required here. A question I get often is, how much data do you need? And I'll give an unsatisfying answer. There's no minimum threshold. There are only trade-offs. This entirely depends on the diversity and variability of the target domain and the level of performance that you need. The less diverse and less variable the domain in which you're trying to operate in, the less data you will need. The more diverse and the more variable, the more data you will need. You've got some tasks you think you might be good candidates for machine learning, and you've got some data you might be able to leverage. Leadership is starting to consider machine learning a strategic priority for the company. All of the pieces are slowly falling into place. Often timing of starting the initiative will come down to when you manage to find the right people. If you find the right people, it's probably time to put things into motion. One thing to be aware of is that the right people won't want to join unless you demonstrate that leadership is 100% bought in and willing to invest. Also, your data set needs to be high quality. If they see your data is a mess, talent is going to run in the opposite direction. I personally joined integrated projects because they presented a vision where automation becomes a core competency of the business. And we had a vision of not only automating floor area estimation, but automating the entire Scan-to-BIM process. And we have one of the largest Scan-to-BIM data sets in the world. It's extremely diverse with data from every piece of laser scanning kit on the market, from every conceivable type of facility. And this diversity in the training data is so important if you want the resulting machine learning model to be robust. This data set is also super standardized and super clean. Early on in the company's history, the founding team decided not to negotiate with customers about how to model. There's no discussion of LOD or families or naming. We have a standard execution plan, and it's a take it or leave it proposition. This has allowed the company to scale, but it has also made our data set really easy to exploit for automation. I was talking to Jose about the kinds of people that we would need on the ML team. Early on, there are going to be generally two functions that need to be filled. There's the machine learning scientist who invents the system that you need, develops a working prototype. And then there's the machine learning engineer who takes the prototype and packages it into a production pipeline that can be deployed in your application or in the cloud. These are the skills that you're going to be looking for. And I mean, I'll be honest, finding someone with all of these skills and knowledge is tough. You're probably going to have to work your way into PhD labs at the universities to find these kinds of folks, but they are there. You'll be probably competing with big tech to attract them, so you're going to have a very good story. No candidate is going to be perfect. Ultimately, you just need someone that has the courage to give the problem 100%. The first thing we did after assembling the ML team was to draft our first automation roadmap. The roadmap is all about striking the perfect balance between complexity and resources. There'll be content talking about objectives, milestones, incremental development, and clear ROI. The big question is like, how do we start with something low risk, like floor area estimation, prove out the competence of the team before tackling something more audacious like Scan-to-BIM? What started here as a conversation about automating a standard business process, floor area verification, quickly evolved into a discussion about automated building measurement services and reports. In our excitement, we really went deep on floor area measurement standards, understanding every nuance of all the different area types. We played around with the data to see how it could be reconfigured to meet the demands of the complex floor area standards. Boundary areas seemed to be no problem, but doing things like space classification and wall priority would pose a challenge. Maybe we could combine some of the things that we had, or use a state-of-the-art language model to cobble together enough signal to approach this. So ML and AI are all the rage right now, and there are shiny, distracting objects everywhere. For us, a simple question of how can we automate floor area verification when we accept Scan-to-BIM projects quickly became, how do we generate millions of dollars in additional revenue by offering a fully automated building measurement report built on top of all of the fanciest new tools? This is just an example of how easy it is to lose focus. And this continues to be one of the hardest parts of my job. How do we, as a small, lean automation team, stay focused on practical, solvable problems and not get distracted by the almost infinite opportunities available to us. Once a reasonable roadmap is put together, we now design the system. These are some of the guiding principles that we used when approaching this. Start with the simplest solution first. Use off-the-shelf technology when possible. I also suggest using mature technology whenever possible, because you'll read some paper with some new state-of-the-art algorithm and you will be tempted to use it. But I warn you, the way performance is reported can be a little misleading. It'll work really well on the author's data set, but when you try to implement it, it just won't perform well. I suggest instead using the types of algorithms and models that have been around for 5 years, that keep being used and deployed and have proven their performance in a multitude of environments. Those are the things that increase your chances of success. I would also say you should be mindful of open source licenses. Because just because you have access to the code doesn't necessarily mean that the authors allow commercial use. For our floor area estimation task, we had several options. 2 are here. Do we frame this as an image processing task or a point cloud processing task? We did some testing on both, and we decided to use the more mature technology, which in this case was the image processing. Let's talk about some development challenges. The point cloud projection script we wrote was taking a really long time to execute, and we were generating hundreds of thousands of these kinds of images. This meant that generating training data would take weeks, which in the case of development slows everything to a crawl. Ideally, we would speed this up by 10, if not 100x. We had to go in, optimize the code, and we achieved that kind of speed up. Another challenge. So when we first started generating training data input and output pairs, we discovered that the model and the point cloud weren't aligning. And because they weren't aligned, they just didn't work as input and output pairs. This problem here was an existential threat to the entire automation initiative. If we couldn't figure this out, our data set was essentially useless for automation, and we would have to go in and manually turn, rotate, translate every single sample. We did manage to recover from this by extracting transformation information from thousands of Revit files using some tooling. But it was a huge relief when we figured this out. Another challenge we faced was something that comes up in training data design all of the time. That is class imbalance. An important distinction for our floor area estimation neural network to make is between indoor and outdoor space. Our data set, unfortunately, was 90% or more indoor space. And when a data set is this imbalanced, like 90% plus a single type of class, in this case, indoor space, and a small minority of outdoor space, it becomes difficult to train the neural network to allow it to learn about the underrepresented class. In this case, we performed some class balancing just to even out the representation. A few of these challenges just give you a sense of how data is probably the hardest part about machine learning. Even in the case of our immaculate data set, we were still running into massive issues that threaten the viability of the whole effort. Another problem is there is going to be constant tension between do we continue to improve performance of something that we've already developed, or do we move forward and develop new features and capabilities? One of our early neural networks was exhibiting a really noisy boundary around its prediction of floor area. And for us, this was unacceptable. So we had to go back into the training data set and add a separate class, which you see in lime green here, which was our floor area boundary class. And this just forced the neural network to pay particular attention to the boundary. With machine learning, there are no guarantees. It's not going to be perfect. When you talk about performance, I much prefer visuals over summary metrics. An accuracy figure doesn't tell me a whole lot about the failure cases, like why is it failing, in what context is it failing, just so that I have a better understanding of what is causing the loss in performance. I think as much as possible, you should try to reveal what is going on inside of the black box. Like for pretty much every project the floor area estimator processes, it outputs visualizations like this. So the folks that rely on it can quickly open up these visuals, verify that things are working as expected. This is one example where floor area estimator is failing on an indoor basketball court. So we finished development. Results are looking great. My floor area estimator prototype system was packaged into a production pipeline and deployed to the cloud to automatically process every project we receive. Almost immediately, we start to get complaints from our modeling partners that floor area estimates are all over the place. In some cases, many times the real value. When I went into the visualizations, I saw this. This is not what I was seeing in my development environment. And it's frankly just enough to make you go mad. When I was working on my computer, it looked fine. And now when people are relying on it, everything is just failing catastrophically. In our investigation, we noticed these horizontal and vertical black lines in our point cloud projections. And these were new. I hadn't actually seen these in the training data or during any of the development. So we tried to diagnose what was causing this. I thought maybe it was some interference between the projection script and maybe the way that point clouds were being subsampled. But that ended up being a dead end. Turns out, in an effort to save on compute cost, we did some optimization to the code where we were reading the point cloud in as floating point half precision instead of single precision. It's kind of a nuanced point, but it shows you just how fragile these systems can be. And because the training data didn't have this pattern of vertical and horizontal black lines, the neural network just didn't know how to respond to them when it saw them in our production system. These kinds of differences between the training data and the domain where you deploy the neural network into is always going to be there. Like the two are never going to be identical. In our case, it was like an optimization difference, but in reality, there are like a million sources of this. Like what happens when a new LiDAR device comes out on the market and the type of data it collects now differs from all of the data within the training set. Because the world is constantly evolving, you're always going to have to retrain these neural networks to maintain their level of performance. Now that floor area estimator is reliably working in production, we have our sights set on the next challenge. BIMit is our Scan-to-BIM service. and we're working to automate as much of the process as possible. A lot of what we did with floor area estimator laid the foundation of infrastructure for this next phase. This is an early production test we ran back in the spring. It shows a side-by-side comparison of manual modeling and automated modeling. We have since moved away from using a Revit plugin. We now do all this processing in the cloud using the design automation API. We're calling the product BIM at first draft, and it's supporting all of our Scan-to-BIM. So we're probably going to be releasing BIM at first draft to customers by the end of the year. I encourage you all to reach out to us if you want to join our alpha program. And if you want to talk about anything AI, machine learning, Scan-to-BIM, just add me on LinkedIn. I'm always happy to chat. Thanks, everyone. That's all I got.